Louis Ferroni. So,
okay, thank you for the introduction and thank you all for attending. The title of this short talk is Chow Polynomials of Matroids or posets, if you will. And I will try to make it amenable and accessible for most of you. So I will try to be very concrete with the objects I will define. If there are questions, please interrupt me, it's fine. So throughout my talk, I will have the poset P. For me, P is a finite poset, so I have finitely many elements. Let's have as an example this diagram. In combinatorics, it's very typical to, whenever you have a bounded poset, namely a poset with a minimum element and a maximum, called the minimum 0 hat and the maximum 1 hat. The hat is just not to get confused with digits. And the rest of the elements you can label in any way. I will just use some letters. Typically, when I will use variable elements of my posets, I will use the letters S and T. So typically, when you have a poset, you can define what is known as the incidence algebra of the poset over a ring, whatever ring you want. I will tell you what the elements of the incidence algebra are without actually defining the incidence algebra, and you will understand quickly what this is all about. So consider the matrix where I label my rows with the elements of my poset, and I do the same with the columns. And I will allow non-zero entries only when the label of the row is smaller than the label of the column. So in particular, 0 is smaller than everything here, smaller or equal than everything here. So I am allowed to put non-zero entries in all these asterisks. With A, I can do the same, but there's one exception, which is 0. So I can do this. With B, I can only compare B with 1 and with B. So here I cannot put something non-zero. And with C, I have this situation. So whatever doesn't have an asterisk is always by definition 0. So my asterisks are polynomials with integer coefficients and variable x. So the idea is that whenever you have two objects of this form, if you sum them, you will end up with an object of this form. If you multiply them as matrices, the same happens. And a typical element of this form is called an element of the incidence algebra of P over this ring. Now, quick observation. So note, so if you multiply two of these things, you will end up with a thing of the same shape. If you take inverses, whenever you can, the same, you will end up with something of this shape. When can you invert? Well, essentially when all these elements in the diagonal are invertible in this ring. So my only invertibles in this ring are 1 and -1. So note, a matrix as before is invertible if and only if the elements in the diagonal are plus or -1. Okay, so this is a common setup. Now let me restrict to a special class of posets, which is still very important, which is graded posets. Graded means that essentially you have a notion of level 0, level 1, level 2, and so on. This is the case here. So I have my bottom element at level 0, A at level 1, B and C level 2, and the top element is level 3. So whenever you can do that, you can define, so if P is graded, one can define the so-called characteristic polynomial. Yeah.
Two elements at the same grade, they are not comparable, I guess, but two elements at different grades, they must be.
No, not necessarily. So, yeah, for instance, well, in this case, it's what you say, but you can have more pathological things.
When you're doing matrix multiplication, are you doing combination on the instance algebra?
Well, what's there? Yeah, that's a product of the instance algebra, which is normal for most people known as convolution. Yeah. Yeah, so whenever I have a graded poset, I can define the characteristic polynomial. What is that? Well, something that essentially records a numerical invariant with many features. So one prominent example of a class of graded posets and characteristic polynomials are if P is the bound lattice of a graph G, then the characteristic polynomial is the chromatic polynomial of G.
Is the bond lattice?
So the bond lattice means that if you take your graph G and you consider all the partitions of the set of vertices that have the property that whenever you restrict one component, you get a connected graph. So you can order all those partitions upon coarsening, and that's the bond lattice of the graph. If you know about matroids, this is just the lattice of flats of the graphic matroid associated to G. Yeah, so my point here is that whenever you have graded poset, you can define a polynomial that is very special, but this is not a trivial object because, for instance, if you take a planar graph, this polynomial will be modeling the chromatic polynomial, and it's a notoriously difficult problem to prove that for planar graphs. If you evaluate this polynomial at 4, you get not something that is non-zero. So, non-trivial object. I'm skipping the definition because it's not necessary.
And what is the degree for the bond lattice?
What, sorry?
What is the degree for the bond lattice?
What is the ordering? Coarsening. So you coarse because it's partitions of the set of vertices. So you
You
can.
have the order, but you need the grading also.
Yeah, but I mean, when you draw the poset, you realize that the number of components is yeah. So, well, this is the object. Now, what I want to tell you is the following thing. So there is a further object called the reduced characteristic polynomial. So definition. Reduced characteristic polynomial of the interval St of P is chi over line St. So I will, for every pair of elements that are comparable, define this polynomial as the characteristic polynomial of St divided by x minus 1. You can always do this because a property of the characteristic polynomial is that if you evaluate this in 1, you always get 0, so you can factor out this thing. But this is only possible whenever S is different from T. But I will define this as minus 1 when S equals T. So I have defined an object on all intervals, which in terms of matrices would amount to saying that I have a matrix in this form, and I have minus 1s in my diagonal. Is that clear? Now, my definition is that, so consider the element H defined as, take this chi overline. This is invertible because the diagonals are minus 1. I have a new matrix if you want, and I plug a minus so my diagonal has 1s. This is a new object. So whenever you give me an interval of the poset, say ST, I can compute some polynomial. It will be a polynomial, and that's called the Chow polynomial. So let me write that here. So HST is called the Chow polynomial. Of ST. And yeah, one theorem, which is already very tricky.
One
So,
question
yeah.
for you. Obvious that it depends only on the interval ST? Because I guess it's true.
Yeah, that happens. You can refine this theory by adding, instead of grading, a weak rank function, and then you can lose combinatorial invariance, and very subtle things can happen. But what I'm telling here, yeah, it will only depend on ST. So you give me an interval ST, and it will always be fine. And if you give me two intervals ST that are isomorphic as posets, you get the same result.
Yeah.
Yeah. So theorem. I have written this definition without restricting my class of posets to something that has a particularly nice characteristic polynomial. For instance, June, with his collaborators, proved that if your poset is not only graded, but actually a geometric lattice, which is like a special kind of graded posets, then the characteristic polynomial, and furthermore, the reduced characteristic polynomial, has log concave coefficients. It's been known since Rota's work that characteristic polynomials of geometric lattices have a property that is very special, which is that the signs of the coefficients alternate. So there is a sign definiteness for characteristic polynomials of special posets. I am inverting this element, so I don't expect any sign pattern to appear in this H. But the theorem is that it does appear. All the coefficients of H are positive. So theorem, so HST has negative coefficients. Furthermore, the degree of HST is always equal to the degree of T minus the degree of S minus 1. HST is palindromic. So essentially the coefficients read the same backwards. So for instance, a polynomial, an HST can look like 1, 2, 1, 4, 6, 4, 1. That's fine. Yeah, the interesting thing is that whenever you have a geometric lattice, this is a shadow of Poincare duality in a special ring associated to the matroid. And yeah, and there's one more thing that I didn't tell you, which is that HST is unimodal. This last property also follows from the Kähler package for Chow rings of matroids when the poset is a geometric lattice, but this is true for all graded posets. And this is a sort of numerical shadow of hard Lefschetz. The proof here, and actually the full setup.
Just one question. When you say unimodal, you mean the coefficients are unimodal or
Yeah,
the values of
the coefficients are unimodal. Yeah.
He has only 1 minute or more, so let's let him speak.
Yeah, the coefficients are unimodal, meaning that they grow up to a point and then decrease, but palindromicity will guarantee that the peak is in the middle. So this property happens for all posets. In particular, you can ask, I mean, what's the technique to prove this? And the technique is actually very, very nice, and it is related to the so-called Kashdan-Lustig-Stanley theory, which associates to special elements in incidence algebras of posets special functions called Kashdan-Lustig-Stanley functions. And what we do is, for any of those special elements called kernels, we associate a Chow function and the Kashdan-Lustig functions, and we make them interact in a nice way. And as long as at least one of the Kashdan-Lustig-Stanley functions is non-negative, you get that the corresponding Chow functions are unimodal. In this case, one of the two Kashdan-Lustig-Stanley functions happens to be 1, and that is giving you the unimodality. So yeah, this is like a friendly and very specific particular case of what we are doing. This is an ongoing collaboration that I have with Jacob Mathern, which used to be a member here, and Lorenzo Vecchi at KTH. And yeah, that was what I wanted to tell you.